Alright, the purpose of this video is to briefly go over some power analysis. Now I do power analysis more extensively in my 620 class, so I encourage you to take a look at the notes from my 620 Moodle classrooms, but this will essentially hit how it can be applied to some of our higher level statistics. Now, what is statistical power? Statistical power is the ability to detect an effect of a certain size. And really what we mean is a treatment effect. So it might be a effect size using Cohen's d, it might be a r squared, it might be a partial eta squared or eta squared, but it's looking for a certain size effect. Often these effects are identified as small, medium, or weak. I mean small, medium, or strong, much like we've been referring to effect size all semester. And we want to know if our design is set up in order to actually detect that effect if it does exist. So if we expect that a certain training program will elicit X amount of strength gains, a medium effect size and strength gains, then I need to have a research design that's organized in a way that will allow me to reject the null hypothesis if in fact elicit that amount of strength gains. So the probability that a test will not find that an effect exists within a population is identified as beta. Therefore, power is referred to as 1 minus beta. So kind of think of this in reference to alpha versus beta. Where alpha is the chance of making type 1 error, the beta is the probability that a test will not find an effect that exists, so that within a population. Essentially, what beta is the chance that you're going to commit type 2 error or accept the null hypothesis. Power is therefore calculated as 1 minus beta. We like to minimize that beta level to be 0.2 or less. Therefore, often we aim for our power to be 80%, or 1 minus 0.2. So the ideal minimal level of power in most studies that we try to achieve is 80%. That is not obviously in direct opposition of alpha, which is often 0.05, but the reality is to make beta exactly opposite of alpha would be extremely difficult to do. To have a 5% chance, to have only a 0.05% chance that we will not find an effect that exists within a population. It would just place an undue burden on most research. So statistical power is dependent on a number of factors. Sample size is probably one of the most dominant ones and probably what most of us associate with statistical power, but there are other things too. Alpha would clearly be one of them, even though that's typically constant in most of our fields. Alpha doesn't always have to be 0.05. Sometimes alpha is 0.01, which would decrease your statistical power. Sometimes alpha is 0.10, which would increase your power because it makes it easier to detect an effect. If you use a one-tailed versus a two-tailed test. A one-tailed test, given that you have enough theory, logic, and literature to set up the test in that way, should increase your power. That being said, more often than not, we run two-tailed tests. An effect size. It's easier to detect a large effect. It is harder to detect a small effect. So you're going to have greater statistical power when you expect that your experiment or your intervention will elicit large effects. It's also something that doesn't really go into the calculation as obviously as everything else is using a within design versus a between subjects design. So using repeated measures variables versus within subject or between groups variables or independent groups. When you are using a person as their own control, you are actually increasing the power because it's going to reduce subject variability. As a result, sometimes one of the ways that we can increase our statistical power is using matched pairs on some parameter. So that will change the statistical analysis. It'll change you from independent groups to repeated measures, but it will increase your power as a result. Now, you can calculate power in a way that can help you out as a researcher. The most typical and most appropriate way to do a power analysis is an a priori. A priori just means pre-planned, and what this is, it's done during the proposal design process or the research design process, where you're trying to calculate the number of subjects or participants needed for a sample in order to have 80% power, an 80% power or chance to detect an effect of a certain size. Typically, we go with a medium effect size, kind of in the Goldilocks theory of, assume the medium level. Although, if you come from a research area that has enough background, you might choose to calculate for a large effect or for a small effect. If that's all you expect in this research area to be able to elicit. If you have a lot of research that says, I'm only doing a treatment that should probably only elicit a small effect, then you would run your a priori analysis for a Cohen's d of 0.2 or a partial eta of 0.05 or 0.06, something along those lines. So a priori is really the most appropriate power analysis to run. Essentially what it does is it makes sure that you have enough, it sets you up to know exactly how many participants you should be recruiting in order to be able to reject the null hypothesis appropriately. Now, we discussed in class, just by adding subjects, you increase your chance of being able to reject the null hypothesis. It gives you power to have more subjects. I'm not trying to get you overpowered. I don't, if a power analysis says recruit, 200 people, if you recruit 600, then yeah, you've probably set yourself up to have a huge amount of power, and you could probably find statistical significance when there is no meaningful significance. What a priori power analysis does is allow you to find statistical significance when meaningful significance exists, if that makes sense. In the planning process, if you're writing for a grant, if you are trying to do your own organization, as we've talked in class, it's a lot easier to get published if you have statistical significance than if you don't. So as a result, a power analysis sets you up for obtaining a statistical significance when, in fact, you should be obtaining statistical significance. So an a priori power analysis really sets you up for the most success. If you're writing for a grant, you almost always have to do a power analysis. A post hoc power analysis is a little bit more controversial. What it does, it's post hoc, so it's done after the fact. It's done after a statistically non-significant finding, and that's what this bullet point down here is saying. Basically, you have now calculated the effect size. SPSS gives you partial eta squared, or you calculate Cohen's d, or you calculate omega squared, or what have you. You take the alpha level that you used, typically 0.05, and your sample size, and the researcher calculates how much power the study had. Now, given that 80% is that kind of ideal level, what this will tell you is, did you have enough power to detect an effect if the effect actually existed? Essentially, it sort of allows you to kind of quasi-explain that if you had to accept the null hypothesis, it could have been because there was no treatment effect, or it could have been because you just didn't have enough subjects to detect that treatment effect. A lot of measurement people will tell you that post hoc power analysis is kind of not helpful at all and not very good. Doesn't mean people don't report it all the time, so it's worth seeing it and knowing what it is. You could always run it for yourself, kind of to make that organization, but I would say that it's less accepted in the literature. So G-Power is a free program that you can download to help you calculate either a priori or post hoc power analysis. Again, separate power from power analysis. Power is just whether or not you can detect an effect of a certain size. Power analysis allows you to calculate either how many subjects you need for an a priori or how much power you actually obtained in the study you conducted. So power analysis, in the past, it's been done using power tables. Those are a little disjointed. Sometimes it doesn't give you all the options you need. It doesn't have all the potential intervals that are needed. So this is where, and Warner has a whole bunch of power tables if you go through her book. I'm a big fan of this G-Power program. the link to download it and the manual is available on Moodle. I use it for almost every single assignment in my 620 class, and I use it in all my research. But let's say you want to conduct a study where your statistic is an independent groups t-test. So we'll start from the very basic. You'll still have, or in order to conduct an a priori power analysis, you have an alpha level of 0.05. You're going to expect a medium effect, which for a t-test, that's Cohen's d, and a medium effect for Cohen's d is a 0.5. How many participants should you recruit to have 80% power? That's the question that we're going to ask with an a priori power analysis. And this is what G-power gives you. And I'm going to increase the size of this visual for you and encourage you to go run this on your own, because you can repeat exactly what I did here, where I told the computer I was going to run a t-test, and I wanted to do a test of mean difference between two independent groups, so an independent groups t-test. I wanted an a priori power analysis. I told it that I was going to use two tails with a medium effect size of 0.5, an alpha of 0.05, and I put in my power at 0.8. Now, G-power defaults at a power 1 minus alpha, so it would default at 0.95. You're going to have to change that to 0.8. And this allocation ratio is just whether or not I would expect to have an equal n. And since that is the general assumption for an independent groups t-test, I am expecting a 1-to-1 ratio, so I'm going to leave that as 1. And after I press calculate, here's what happens. It tells me that I'm going to have a sample size of 64 for group 1, a sample size for 64 for group 2, and I need an overall sample size of 68. And what that will result in is 80% power. So that's, and it'll give me a critical T of 1.98, essentially. So I would need a T of over 1.978, etc., with these groups in order to be able to reject the null hypothesis if I obtained an effect size of 0.5. The visual up here tries to show you that, where here's critical T, here's the power that you have, this is where you'd be rejecting the null hypothesis, here's that alpha divided in half because it's two-tailed. I don't find the visuals very useful, personally, but you might find them helpful. There are other, depending on what statistic you're using ANOVA, MANOVA, regression, and so on, G-power does not use partially to squared for an effect size for ANOVA, but you can calculate their effect size for an ANOVA off of partially to squared. So they use effect size F. Now, that's not, and you can't find that anywhere on SPSS. However, you can calculate it using partially to squared. So it's a to squared or partially to squared divided by 1 over partially to squared or unexplained variance. Take the square root of that number, and that will give you effect size F, where a small effect size F is 0.1, a medium effect size F is 0.25, and a large effect size F is 0.40. Now let's take an example now from the doubly repeated measures MANOVA from earlier in this lecture, different slides. Let's see if I can, again, make this bigger. This is post hoc power. So in that doubly repeated measures MANOVA, what we see here is that because it was a MANOVA, it falls in the family of an F test as opposed to a T test. It was a doubly repeated measures MANOVA, so it's a MANOVA with repeated measures and within factors. I said now I want to do post hoc power, find out how much power was achieved given an alpha, sample size, and effect size. I had to have calculated effect size F using the partial eta squared obtained from my SPSS. I still used an alpha of 0.05. The sample size in this example was 10, where I had 3 groups with 3 sets of measurements, and the correlation of those the average correlation of those measurements was 0.5. So I plug those numbers in, I press calculate, and if I go through here, it shows me that I had a power of 0.91 or 91%. So even though I have a really, really small sample size of over 10, things that are helping me out or increasing my power here are the fact that I did a repeated measures design and that I have a very large effect size. Because remember, a medium effect size for effect size F is 0.25. A large is 0.5. So 0.62 would be considered a large to extremely large effect size in the world of effect size F. So would not be surprising if we, that we rejected the null hypothesis for that example. Other effect sizes, F squared, effect size F squared, is used for multiple regression in the G-power program, where you would use R squared over 1 over R squared to calculate it. So again, it's explained over unexplained, but since this is F squared and not just F, we don't need to take the square root. Small is 0.02, medium is 0.15, large is 0.35. Just in case you were curious, if you put in a priori post hoc or a priori power analysis for a medium effect with an alpha level of 0.05, so let's say we're going to have a medium effect, alpha equals 0.05, and I want to know what my n will be with one predictor. Guess what? Your answer is approximately 25. I think it's 27, but it's right on that number that we were using this fall with the number of predictors k times, or number of predictors times 25 for sample size. Alright, so just to sort of wrap up, that is a quick review. It's worth further studying, ask some questions, but now it's important for you to tie these two concepts or these concepts of power analysis to what you know about type 1 error and type 2 error. So pause this, look at this figure and think about it, and then you can press play and I'll describe a little bit about what I think about how power comes into play with type 1 and type 2 error. So here's where I think you're set up. If you have appropriate amounts of power, you're probably set for falling in these two. You're probably set for falling in these two areas most often. Where if you have enough power, you're probably going to reject the null when the null is false, and you'll probably accept the null when the null is in fact true, because you're either going to detect an effect that exists, or you're going to say, nope, that effect doesn't exist, even though I have a large sample size, so I'm going to accept the null hypothesis. If you are underpowered, which is very common in dissertations, primarily due to just resources, funding, you are most likely to probably commit type 2 error, which means you're underpowered, you don't have enough subjects to be able to detect your effect size. So you're going to accept the null hypothesis, but there's a chance, especially if you look at your effect size, that something was going on. You have a small to medium effect, you just weren't able to detect it, so you might try to make that argument in your results section. So that's type 2 error. Type 1 error, rejecting the null when in fact the null is true, that's going to happen when you are severely overpowered. This is when you just keep pumping up your subjects, up to a point where it's unnecessary. We just keep getting more subjects, and you can detect small, meaningless effects. I hope this was helpful. Please post any questions that you have as you review power. Play with the power analysis program. I encourage you to use it for your own dissertations if you decide to do a quantitative dissertation. It will set you up for the most success in terms of publication and being able to reject the null hypothesis when appropriate.